So hello and welcome to another video. In this series of videos, I'm looking at topical revision at KCSE level, and in today's video, I'm looking at topic number 14, which is in Form 2, and it is referred to as equilibrium and center of gravity. Before we go to the marking scheme of this paper or this worksheet, I'd like you to note that you can download this paper. When you go to the video description, there will be a download link. Just click on it and you'll be able to download this paper into your computer, where you can print it out, solve the question, and then look at the marking scheme as we discuss in this video. The other thing that I'd like you to note is that when you scroll to the end of the paper, you will find that I've started to give links to most of the videos where I feel that you're going to benefit when you're doing your revision. So in this link, you'll just click on it and your web browser will be able to open this video quickly for you. So those are the two things that you need to do. Don't forget to scroll to the end of the last page of that paper where I have given you links. And let's go straight to the marking scheme. So in the first question, you are asked to define the term center of gravity, or COG, of an object. And this is the point of application of the resultant force due to the force of attraction on the object by the earth. This force of attraction on the object by the earth is called the weight of the object. So the point through which the weight of the object passes through or seems to act is what we refer to as the center of gravity of an object. There are two types of objects that we deal with. There are those which are regular and they are irregular objects. In question 2, I've given you regular laminae in the various shapes, regular shapes, like a square. To find its center of gravity, you just need to draw these two diagonals. For a rectangle, again, you draw the diagonals. For a triangle, this is what you do. You divide this length by 2, exactly by 2, so that this point is at the midpoint of this length, and then you join this point to the apex of the triangle on the opposite side. You repeat with this other side here. You divide it by 2, and then you join that point again to the opposite apex. You'll find that you have already identified the center of gravity of the object at this point. And if you want to verify that this is the center of gravity of this object, just draw a line from this apex passing through this point. The point it touches on the opposite line, you'll find that that line also divides this line by 2. How about a circle? All you need to do is just draw two diameters, and the point of intersection of those two diameters is the center of gravity. To draw the diameter from a given point, all you need to do is to draw a tangent at that point, a tangent, and then you draw a line which makes 90 degrees with the tangent at that point. It will pass through the center of the circle, and you produce that line all the way to the other end, and it becomes the diameter. Now let's look at question 3. In question 3, we are given that a uniform metal bar 100 centimeters long balances at the 20 centimeter mark when a mass of 1.5 kilograms is attached at the 0 centimeter mark. Calculate the weight of the bar. And many times all students do is to rush and write F1 times D1 is equals to F2 times D2. You can do that provided you come to the diagram here and identify the forces that you are calling F1 and F2. So, and remember, you are not prevented from marking any values on any diagram. In any case, it makes the examiner know exactly how you are proceeding with the calculation. So over here, I realize that this mass that is suspended at the 0 centimeter mark has a weight of 15 newtons. How did I get 15 newtons? I know that weight is equal to the mass of the object times the gravitational field strength. And that is why the gravitational field strength is given in the question. So when I do 1.5 kilograms times 10 newton per kilogram, I get 15 newtons. The other thing that I observe from the question is that I've been told that this one is a uniform metal bar. A uniform metal bar. What that means is that since it is uniform and it is 1 meter long, then I will divide that 1 meter, which is 100 centimeters, by 2 to get the center point, which is the 50 centimeter mark. And I know this is the center of gravity of that metal bar. And what is center of gravity? It is the point through which the weight of the object acts. So I immediately indicate the weight of the object. So these are the two main forces which are acting on the object. Of course, there is another force which is acting at this point, and it is the reaction force due to this knife edge vertically upwards. But since we are going to take moment about the pivot, which is the 20 centimeter mark, the moment due to that force or any other force which acts through that point becomes 0. So that is what we do. So take moment about the pivot. Before I do that, I need to determine these distances from the turning point, or from the point about which I've decided to take moments. I measure the distance which makes 90 degrees with this force, and that happens to be 20 centimeters, which is 0.2 meters. And then from the 20 centimeter mark to the 50 centimeter mark, again there is 30 centimeters, which is 0.3 meters. So that is all I need to do as far as determination of the distances is concerned. So I'm going to say the sum of clockwise moments about this point is equal to the sum of the anti-clockwise moment about the same point. So anti-clockwise moment is due to this 15 Newton force about that point. So I do 15 newtons times 0.2, and the clockwise moment is due to the weight of the metal bar, which is W times 0.3. And when I manipulate those values, I get 10 newtons. So this is a common question, and you should be able to work it out and get the 3 marks or the 2 marks which are usually allocated to that question. Now let's look at question 4. Again, we are given a uniform metal rule of weight 0.9 newtons. This time the weight is indicated. We are told that it is suspended horizontally by 2 vertical strings P and Q placed 20 centimeters and 30 centimeters from its ends respectively. Calculate the force or the tensions in each string. So the strings are given P and Q, and the tensions in each one of them is F1 and F2 respectively. Again, I realize that since this one is a uniform meter rule, then at the 50 centimeter mark, that is where we mark the weight. So I know from the 0 centimeter mark, this must be the 50 centimeter mark. So this one is 50 centimeters. That means that from point A all the way to the line of action of the weight of the object, it should be 30 centimeters. And similarly, from here to here, it should be 50 centimeters. That means this one is going to be 20 centimeters. So this one is 30 and this one is 20. Now at this point, because the object is supported at 2 points, exactly at 2 points A and B, it is common to take moments about one of the points so that you can eliminate one of the forces which is acting through that point. Like I have already explained, if you take moment about a given point, if there is any force which passes through that point, then the moment due to that force will be 0 because the distance is 0. So we do a clever trick here by taking moments about one of the points so that we can eliminate one of the forces automatically. So we take moments about point A, for instance. So we're going to see that clockwise moments are due to the 0.9 newtons, while the anti-clockwise moments are due to the F2. So we are going to get 0.9 times 0.3 because again we have to determine this distance, which is 30 centimeters, that is 0.3, and we've also got to determine the distance from this point all the way to this point. So observe that although I know that this distance is 20 centimeters, I don't use 20 centimeters because that is not the distance from the point about which we are taking moments. The distance of this force from the point about which we are taking moments is the whole of this distance. And by the way, I should remind you that when you say take moments about a given point, all distances must be measured from that point. All distances which are going to the line of action, which are making 90 degrees with the line of action of the given forces, should be measured from that point. So this is 30 centimeters, where this is 50 centimeters. So again, when I manipulate values, I get this expression here, 0.9 times 0.3, the 0.3, that is clockwise moment, and then F2 times 0.5, which is 50 centimeters, is this distance here. So I get F2 to be 0.54 newtons. Now, in order to get F1, I can use the second condition for equilibrium, because there are two conditions that must be fulfilled if a system of forces is in equilibrium. The first one is that resultant moment must be zero, or resultant moment is zero. That is just like saying sum of clockwise moments equals to sum of the anti-clockwise moments about a given point, because the system is in equilibrium. So resultant moment is zero. And again, resultant force, this is the second condition, resultant force on the system is zero. That means that if you take forces in one direction, for example, if you add the two forces which are acting vertically upwards, F1 plus F2, it should be equal to the sum of forces which are acting in the opposite direction, which happens to be vertically downwards. So I get the expression F1 plus F2 is equals to 0.9. In which case, because I know F2, I just need to subtract that from this and I get F1. And that is exactly what I've done. I got F1 to be 0.36 newtons. The other way would have been to take moments about point B. That is to repeat what I did here. Would say take moments about point B, and I would find that clockwise moments, which is F1 times this distance here, which is 0.5, is equal to anti-clockwise moments, which is 0.9 times 0.2. But this one is a skill which you should be able to get. Let's go to question 5, where we are asked, when is a body said to be A, in stable equilibrium? This is a question that we normally get, and sometimes it comes in form of a diagram where we are asked to identify whether the body is, to identify the state of equilibrium of that body. And you should simply realize that a body is said to be in stable equilibrium when slightly displaced. What should it do? You slightly displace the object and release it. If it returns to its original position, then its state is stable. But when it moves further away from the original position, that is, it topples over, then it is in unstable equilibrium. And if it remains in its new position, then its state of equilibrium is neutral. Remember this. It's a very simple test to determine the state of equilibrium of an object. And this is the statement you should always write down. When slightly displaced and released, then you've got to imagine what happens to that body. Question 6. By determining the position of the COG of the object, determine with reason which of the two objects is most stable. So let's look at the two objects. There is this rectangle here, and there is this triangle. The lines that I've drawn in red are actually the answers that you expect. So first of all, I determine the center of gravity of this rectangle, as we did in the first question, just by drawing diagonals. And I know that this is the center of gravity of the object. And then I know that is the point through which its weight will act vertically downwards. I do the same with the triangle. I draw this median, and the point of intersection of the two is the center of gravity of that triangular lamina. Then I would measure this length of the base. The length of the base is proportional to the area. So when you measure this length of this base and length of this base, you will find that they are of the same length. Let me just insert a grid into this system here so that you can be able to see what I'm talking about. Now we have a grid. Let's see how many squares this base occupies. Actually, it occupies about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I meant this to go all the way up to this particular point, but you can see that, so that when I divide, they don't meet exactly at the center because of this slight displacement there. So when you count the number of squares here, there are also 13. And you find that the size of the base for this and the size of the base for this is the same. So we are left with the height of the center of gravity from the base, so that we can see that this one is much lower than this one. So the position of the center of gravity over here is much lower than it is here. And that means that the triangular lamina is more stable than the rectangular lamina. And that is why I drew this red line here, horizontal line, to show that this height is smaller than that height. So remember, in order to determine whether one lamina is more stable than the other, all you need to do is follow that method. And then the other thing we can do is to determine, of course that one is in the next question, use a protractor to determine the angle. Let me just remove this grid. The next part is use a protractor to determine the angle through which each one can be tilted before it just topples over. And the angle through which this rectangular lamina can be tilted before it topples over is this one here, while the angle through which this one can be tilted is this one. If you are to use a protractor to determine these two angles, this one and this one, you will find that this angle is larger than that angle. Again, confirming that the triangular lamina is more stable than the rectangular lamina. Finally, we've got this question here where we are given the diagram below shows a metal plate 3 meter long, 1 meter wide, and negligible thickness. A horizontal force of 100 newtons applied at point D just makes the plate to tilt. Calculate the weight of the plate. Again, because this one is a uniform lamina, you determine its center of gravity by drawing diagonals. And this is where the weight of the lamina acts. There is this other force which is acting horizontally, the 100 Newton force. So again, we are going to take moments about point A because it's going to turn about point A. The moment due to 100 Newton force will be 100 times this perpendicular distance, which is 3 meters. And the moment due to the weight will be this distance here, which is 0.5 times the weight. And when we do that, when we take moments about point A, we are going to find that the weight of the lamina is 600 newtons. That is for question 7. Let's go to question 8. In question 8, we were asked to state A, 2 ways in which the stability of a body can be increased. And of course, there are just 2 ways. Increase the size of the base support, and number 2, lower the position of the center of gravity. At this point, I would like to mention that when we are talking about the base support, it is wrong to call it the surface area. It is wrong to call it the surface area. And at the same time, when you're talking about the other point, lowering the position of the center of gravity, don't say that you are increasing the center of gravity of the object. That does not make much sense. Of course, here there is a typing error. Let me just correct that. So those are the two ways of increasing the stability of an object. Part B, two practical applications of stability would be in the manufacture of vehicles and in the construction of, say, and number two, in the construction of furniture or in the construction industry or the manufacture of items such as Bunsen burners, beakers, seats, and so forth. The ideas expressed in stability or mentioned in the study of this topic are made use of. And one of them is to increase the size of the base support, and number two is to lower the position of the center of gravity. And these are some of the questions that I would tend to think that they are important in this topic, which is equilibrium and center of gravity. So go right ahead, download the paper, and go to the end of that particular paper. There will be more links to important videos, including this particular video. So I keep on updating this list. As soon as I make a new video, I update the list. In future videos, when you download the question paper from the video description, remember to go to the end of the paper where you will find more links for videos which are going to help you in your revision process. So continue working hard, continue revising hard, and I continue to wish you all the best in your work.